Just a quick lesson on stars. Stars are giant balls of hot gases that emit various forms of energy on the electromagnetic spectrum. We compare the luminosity, that's a measurement of how bright a star is, and we compare it to that of the sun. The brightness of a star depends on its luminosity and its distance from us. Sirius is the brightest star in the northern sky. It's in Canis Major. The color of a star depends on its temperature. Blue is the hottest, red is the coolest. You can see there's a hot star there, and these orangey red ones will be the cooler burning stars. Yeah, I can leave it at that. Every star has a life cycle, beginning, middle, and end. Usually lasting billions of years. They always begin their lives as a nebula, and that's just a huge cloud of dust and gases, but it's mainly hydrogen. That's the key ingredient for a star. And basically, what happens before I read this last paragraph is if you've got, a hydrogen here and a hydrogen here, they will have very little gravity between them, but there will be some, because Newton's law of gravitation says that all matter will attract all other matter with the force of gravity. Now, we live on a huge chunk of matter, and that's why we feel gravity so strongly here on Earth, because the Earth's mass is 6.38. Wait, is that right? No, 5.98 times 10 to the 24, 10 to the power of 24 kilograms. So that's 598 and 22 zeros, kilograms. So gravity's pretty strong. Two hydrogen atoms, gravity's not very strong, but it does exist. So those hydrogen atoms will drift together, clump together in the absence of any other forces, and there is no other forces there in deep space. So they stick together, right? And then this hydrogen will stick together, and then this hydrogen will stick to it. I got to draw hydrogen. But eventually you've got a nebula, a big cloud of gases, and the more hydrogen that sticks together, the more mass. Even though hydrogen's light, it has mass. The more hydrogen that's there, the stronger its gravity will be. The dust and gases swirl around, breaking into clumps and contracting. Stronger the gravity is, the stronger this gas will contract due to gravitational forces. And that kind of chunk, that clump of contracting hydrogen gas is called a protostar. They begin to attract more particles, and eventually the clumps are dense and hot enough as they're clumping and compressing more together. They get hotter and hotter and hotter until eventually hydrogen fusion begins. And what hydrogen fusion is when two hydrogen atoms press together so hard that their protons will join together and make helium. What's helium got? Helium's got two protons in its nucleus. Hydrogen has one proton in its nucleus. So hydrogen fusion, nuclear fusion, is where you stick two hydrogen atoms together, compress them together so strongly and with so much energy that out the other end comes helium. At that point, you've got a star. Once hydrogen is being compressed so hard that it's turning into helium, it releases massive amounts of energy. And this is kind of, these are kind of background radiation pictures of what's going on there. So, nuclear fusion is hydrogen atoms fuse to form helium. And when they do that, they release enormous amounts of energy. And that energy radiates in all directions in the forms of everything in the electromagnetic spectrum. That includes X-rays, gamma rays, heat, light, infrared radiation, ultraviolet radiation, I know you're familiar with, radio waves. I might be forgetting a couple, but I've hit most of them. And that radiation causes it to glow with visible light. The more massive the star, the shorter its life cycle, which might not make sense at first because you think, well, a more massive star means it's got more hydrogen. More hydrogen means you can do more nuclear fusion. But it happens so quickly in a massive star because it's being compressed with so much more gravity. Billions of years after forming, a star begins to burn out as it reaches the end of its life cycle. Why does it burn out? Because it runs out of hydrogen. Basically, once it runs out of hydrogen, it starts fusing the helium and making heavier and heavier elements, iron and things like that. Eventually, there's not much more hydrogen left, and instead, a dense helium core, and the core contracts and becomes a red giant. When nuclear fusion stops and the layers begin to drift away, it becomes a white dwarf, and finally, it even stops emitting energy altogether and just goes out. This is a picture of a supernova, and this would be like our sun and slowly turning into your red giant. Oh, that's the last slide. Do I want to say anything else about the life cycle? Well, yeah, kind of. That's not the only thing that can happen, is why I wanted to mention that, is what our star will likely do is go through that cycle. It'll turn into a red giant, then the layers will drift away and it'll become a white dwarf. That's what our sun's going to do. Our sun is classed as a medium-sized star. It's kind of like a medium star, medium size, medium brightness compared to all the other stars that are known. And so it'll go through that normal life cycle. A little bit more massive star than our sun, and instead of just turning into or swelling to a red giant and the layers drifting away, what happens is they go supernova. And here's your picture of your supernova, which is that big explosion. Instead of the layers drifting away, it blows up very violently. And our sun is not going to do that. It takes a more massive star to do that. And then what happens after that is you are left with a dense core, and that would be called a neutron star. You guessed it, it's made mostly of neutrons. And if you get an even more massive star still, then instead of, it'll still go supernova and all that, but then it'll go to something even smaller and denser and more powerful. I don't know why I drew it in red, because it can collapse into a black hole. A black hole is kind of like a neutron star or a white dwarf, except for it is so dense and has so much gravity that even light cannot escape it, that's where it got its name, a black hole. So those are kind of the possible outcomes, right? Red giant and then to white dwarf, or supernova to neutron star, or you can go supernova to black hole, right? And I don't know if it's at the end of this lesson or the next one, but eventually I do want to show you a video on black holes and also on star stuff and star formation, okay? So let's keep these annotations. I want to just have a look at what else I want you to do in this life cycles of star stuff. So yeah, I've got the, I don't know why I just moved that into ecosystems. That's not a good idea. Let's move it right here. So you've got this lesson on stars and the life, just the basics, bare bones life cycle of a star. And then I want you to read section 9.2. Just read it. Talks about luminosity and the brightness and distance and brightness, magnitude, apparent magnitude, star color and temperature. And they give you some examples. They show you the electromagnetic spectrum and the mass of a star. So it's good stuff. Don't need you to answer the questions. Just read through the section. Email me if you have any issues with that. Then I also want you to write. I want you to watch this program 1 star stuff, and it's a long video, but like I'm not going to be testing you on this. Just put it on and just kind of just to get you interested in this space stuff. All right, it's pretty good. It's pretty entertaining, and I think that you'll like it. All right. So after this lesson, read through the section, watch the video, and then your work is done on life cycles of stars, okay? I think that about does it for me for now. I'm signing off. Don't forget to email me if you have any questions.